the 3 programs that are available to SciDome owners. Oh, good, look, it's people. I love seeing people. There's 3 programs that I wrote in collaboration with my very good friend Dave Steelman, who also helped me write Binary Maker, which is the software I sell commercially. And the 3 programs we're going to go through are Epicycles, Newton's Mountain, and Tides. These are all interactive programs that we designed to work on the dome. Tides also works with SciTouch in a very cool way, but they're all easily manipulable through the console in your SciDome. The versions I'll be showing you today will be the versions that are for the desktop, but they have all the same functionality. And there are 3 handouts in my handouts. One's called Epicycles Dome, and one has to do with Newton's Mountain, and the other has to do with Tides. So all the information, in fact, a lot more information than I'm going to give you this morning, are in those handouts, all about the programs, the historical background of them, et cetera, et cetera. So if you want to have those on, you can, but you don't have to. I'm going to share my screen and we'll go through the programs one by one, give you an idea of what they can do. So you should all see my desktop, which is really exciting. So here are the 3 programs. So let's start Epicycles. And again, if you have any questions, feel free to blurt them out. I'm not afraid of interruptions. I teach college students, so they are not hesitant to ask questions once they get to know me. So Epicycles, I don't know if you know a lot about Epicycles, but you could picture this on the dome. This would be at the zenith, and that's the Earth. And let me zoom in. Everything I'm showing you can be done on the dome. So zooming in and all that stuff. So there's the Earth, there's the moon. And as you well know, you can't just have stuff in space not attached to anything because it'll all fall to the Earth. So everything has to have a solid crystalline sphere. This is what the ancients believed. So everything is on a solid crystalline sphere. Like the emperor's new clothes, you can't see it, but it has to be there. And they have little, or not so little, spheres which also turn on the bigger spheres. The bigger spheres were called deferents, and the little ones are called epicycles. And that was to take into account the strange retrograde motion of the wandering bodies in the solar system. You might wonder why we have 7 days in a week. The reason we have 7 days in a week is because there are 7 bodies in the skies that move relative to the stars. If you don't believe that, ask yourself what are the names of the days of the week and what are they named after? And they're named after those 7 bodies: the sun, the moon, and the 5 visible planets. That's why we have 7 days in a week. So how did the ancients explain everything with the Earth at the center? By the way, down here at the bottom, as you'll see in a few seconds, this is going to be what you would see from Earth, the positions and motions of the planets and the moon and the sun relative to each other. They're going to dance around. On the dome, this actually goes around the circumference, the periphery of the horizon on the dome. That's kind of a cool thing. There is an interface up here which allows me to turn things off. So if I want to just concentrate on the inner bodies, which I'll be doing in a second, I can shut off the outer ones so they don't confuse us, confuse the cat, and so on. So I'm going to zoom in to the inner part of the solar system because there's things to learn here that most people don't know. I'm going to turn off the outer guys. So we've got the sun, Venus, Mercury, the moon, and the Earth, which of course we know doesn't move. The sun and the moon do not have epicycles because they never retrograde in the sky. Mercury and Venus have to have epicycles because they do go back and forth in the sky. So what I'm going to do is I'm going to just start the motion so you can see the guys. I'll slow it down a little bit.
Dave, can I ask a quick question?
Yes, please do.
The ancients understood Mercury to be closer than Venus.
No, I'm
just
getting to
because of
that. That's a very good. Thanks for bringing that up. They did not.
but would they have seen the model this way, and would they have put
Yes.
Mercury closer to the Earth?
Yes, this is so. Yes, let me explain that, and I explain that in the handout as well. I'll explain that once I explain something else. All right. The order of the bodies in the solar system is an order of speed. The idea was that the bodies that are furthest from the Earth, they look like they're going slower. That's because they're further away. That was the way they reasoned it. They had problems with Mercury and Venus. And so I want you to watch. This is what I do with my students. I'll set this going and I'll say, do you see anything strange about the bodies, especially Mercury and Venus? You see anything that's kind of systematically odd? It's the way they move. If so, let me know. This is going to eventually address Scott's question.
Are they rotating on their smaller circles at different rates?
They indeed are, and that in fact is what they need to do. So the epicycles are turning at a different rate. But there's something more, it's smacking you in the face.
Well, they're not going to, the retrogrades are not going to occur at the intervals at which they actually do occur.
Actually not. You can model it fairly well, even though it's circles.
Right.
But there's something else going on. And again, if you watch the bodies, I don't know if you can see it down here, but Mercury and Venus are going back and forth. And they're going back and forth around the
sun.
Yeah, let me
or maybe not.
Let me draw the Earth's sun line. Now it should become more obvious. Why is the epicycle of Venus and the epicycle of Mercury locked to the Earth's sun line? That should have been the first question you asked the ancients. Why does that have to be? And the answer is, the model doesn't work unless it does. If they watch the bodies moving, and they always seem to hover around the sun. Now, obviously, we know why that is, but the ancients, with this, they already assumed a priori that the Earth isn't moving. So this is the only way to make this work. The epicycles of Mercury, the epicycle of Venus has to be locked into the center of the sun, because it looks like they're going back and forth across the sun. Does this make sense? So the question is, why is that? They had no answer for it other than to make the model work, you've got to keep those epicycles locked in with the sun. Now, the other thing that's interesting, how long does it take the sun to go around the Earth?
A year.
Right? That's 1 year, right? Okay. So how do you decide, think about this now, how do you decide where to put Venus and Mercury? Because don't they also go around the Earth in a year? If they're locked to the Earth's sun line, their epicycles also go around the sun in a year. Do you see the problem? How do you decide the order of where Mercury, Venus, and the sun are if they all go around the Earth in the same amount of time? You see what I'm saying? This was a big debate to the ancients. They didn't know. They argued about this order because of that. They decided on this order because Mercury goes around faster in its epicycle than does Venus, and the sun doesn't have an epicycle at all. So in terms of the speed of the body in the sky, Mercury moves faster than Venus. Venus moves faster than the sun. That's why they decided on this order. Does that make sense? Scott, does that make sense?
It does. I just hadn't thought that to them, the orbit was the epicycle. To us, the orbit is its position around the Earth, but to them, it's just its epicycle speed. Am I describing that right?
No.
Their
speed, it's a combination of the two speeds.
But Mercury's rate over a year for us appears to be the same essentially as Venus's rate. So the only thing that's different between the two is one has a faster epicycle than the other.
That is
Okay,
correct.
that's what I'm trying to
Yes.
say.
Yeah, that's exactly right. But you see what their problem was. Their rates of going around the Earth were the same, right? Mercury stays with the sun as does Venus, so they each have a year. But you're right, the rate of epicycle is different. He's going faster. That's why they put him closer to the Earth, because they figured that motion looks faster because he's closer to the Earth. That was the argument. I'm not saying it's a good argument. That was their argument. That's the way they came up with it. Okay. Again, this is stuff that's not taught. People don't, I'm trying to get my students to think. If it's an order of speed, Mercury and Venus, this is sort of arbitrary where to put them since they go around the Earth in a year. Now, what also is sexy about this is that you can have these guys leave breadcrumbs. So let's let Mercury leave breadcrumbs. By pulling this slider, you can actually let it trace out then its retrograde path, which you'd see from the Earth. You can make that shorter or longer, whatever you want to do. You can also do it for Venus. And of course, the sun and the moon don't have epicycles. Or you can just zoom in on Mercury or whatever. So that's kind of fun. Okay, you ready for the second part? So that's the sun, Venus, and Mercury. So let me stop the motion. Let me take those lines out. Let's go back out and let's put on Mars, Jupiter, and Saturn. I'm actually going to turn off the moon, and just so we won't get confused. Now, if I speed up the motions now, we'll make them go a little bit faster. Next question. So take a look at how things are moving. This is obviously Mars, Jupiter, and Saturn. The order of these was never an argument because Mars goes around much faster than Jupiter, and Jupiter faster than Saturn. But there's something systematic going on here, and I'm going to help you. I'm going to put a line from the center of the epicycle to the body, these little radii of the epicycle. And I want you to watch how they're moving and see if you can see something systematic here. See if you can notice something systematic going on in the way they're moving. Yeah, go ahead.
Yeah, oh, I'm sorry. Their angles are all identical. All the radii are parallel to each other.
And parallel to what else? They are parallel to either. You're exactly right, and they're parallel to the Earth's sun line. You notice that?
Yes. Right. Oh, yeah. Mm-hmm. That's what I meant by each other. But yes, you're right. They're all parallel to the Earth.
No, you're exactly right. They're all parallel to each other. Now, if you had asked Ptolemy why that was, do you know what he would have said? Because
right.
That's what makes that. Otherwise, the model doesn't work.
Right.
This is a systematic thing that can't be explained other than it has to be this way. That is a telltale sign that there's something messed up with your theory.
Right.
You're missing some kind of piece of information. In this case, the reason that they're lined up is because the epicycle, of course, is determining when retrograde motion happens. Retrograde motion is a function of where the Earth is relative to the sun and the planet. And so this line, when it lines up, that's when you're starting to see the planet go backward. And so these lines are parallel because they determine when you're going to see retrograde motion. And again, you can make trails. You can see the funds like spirograph. Right, because Jupiter and Saturn retrograde fairly often because it occurs when the Earth goes around in a year and the planet hasn't moved very much. Right, Saturn takes almost 30 years, Jupiter 11, and so these retrograde loops occur very frequently. Mars, not nearly so frequently because we don't have opposition and stuff for like 2 years. If you want to see Mars Mars retrograde loop. Looks like a Lima sun. So what I find is the students, when we go through this, I like them to try to come up with what Chris just came up with, that the Earth-Sun line is indeed parallel with each of these. See, again, this is something that's not taught, because frankly, most people aren't aware of it. And what I'm trying to show you is that this model had these systematic things in it which couldn't be explained. In other words, saying it makes the model work is not an explanation. And so it should have tipped them off that, gee, there must be something fundamental that this is describing. And what it's describing is you got the wrong model. You need to replace the sun and the earth, and then things get better. So this should have tipped them off that there was something they were missing. But it is quite ingenious. And again, as I said several times during Institute, if you saw this on the dome, you would be very impressed. And it's kind of fun to have all the planets down here moving back and forth. If you watch like Saturn, you'll see Saturn, and what Saturn is doing here, it's going backwards and matches this. Now it's going to go prograde again. So it's kind of fun to watch how they move back and forth along the periphery of the dome. So that's epicycles. Any questions about that?
Just one day.
Yes, Scott, go ahead.
Go ahead, please.
I was just going to ask, how do we put these up on the dome? Are they up as like slides or movies when we're like putting them in?
No, it's an interactive program. It does not come automatically with side dome. You have to pay a little extra to get it. And the reason I didn't just give it to Spitz the way I normally, go with the curriculum, because this took us several years to develop. This is a much more involved process between two people than the full dome curriculum. And so we worked out a licensing arrangement where typically what people do is when they buy a new side dome, they'll spend an extra several $100s and get the 3 programs. You can buy each one separately or all together as a package. I forget, Scott, what the actual price is now. It's like $250 per program.
You're in the range. I forget, but yeah,
it's something like that.
And then a little price break if you buy epicycles, Newton's Mountain, and Tides. There's a little discount for buying all 3 at once.
But Emma, this is software that interactive, so you have control over all these things. It's not a movie or a slide. It is an actual program where the stuff all of it gets projected up onto the dome. Okay. Any other questions about this, or we'll go to Newton's Mountain next? Go ahead, Chris.
Just one question, and I can see how involved this has to be. Have you considered demonstrating epicycles on top of epicycles? I know that makes it a whole lot more complicated, but my understanding is that's what Ptolemy eventually had to do. He had to to get Mars to line up exactly with.
It's worse than that. I mean, what he had to do is start displacing the deference.
There, yeah. Right.
Called the eccentric. So he's starting to approximate ellipses by having a circle off center.
Right.
Then Ptolemy invented the equant point, and that was just like bizarro world. So no, we haven't put any of that stuff in. This is complicated enough for my students. I would like to put those in eventually, but they're not in at the moment. I have a life I have to lead.
You don't say.
Believe it or not.
All right, thanks.
Okay, let's go to Newton's Mountain. So when Newton published Principia, most people were not intelligent enough to read it. And those who were realized that it was a complete revolution, literally, in science. It really was the foundation of what we now call classical mechanics. But in order to try to get more people to understand what orbits were, he published a treatise of about 96 pages. I forget the name of it. It's in the handout. But this diagram was in that. This is not in Principia. This is in that little treatise that he wrote later. And this is the Earth. You can see the continents. The sea is for the center of the Earth. And this is better known as a humongous mountain. To scale, this would be about 800 miles high. But we're gonna put a cannon here and we're going to launch cannonballs at different speeds. So this is where we're doing an animated version of what he drew in this little pamphlet that he published. Down here we have, this is the X speed, this is horizontal, and this is vertical. So you can actually shoot the cannonball at different angles. We're not going to do that, but you have that option. You can fire it, you can stop it and clear them off. And then this is how fast the projectile goes in terms of being drawn. Now, when I fire this, it's going to make a noise. So if your speaker is really loud, it could break your eardrums. So just, I'm warning you, okay? So just be careful. You might have to turn the sound down a little bit. Let me just launch this thing. And so when the cannonball is launched, what's it going to do? You tell me. What's the cannonball going to do?
Hurt people and knock down castles.
Yeah, it's going to fall, and it falls because why? It's not a trick question.
I'm going to go out on a limb here and say gravity.
Gravity, yeah, whatever that is. Yeah, there's this magical pull. The Earth is trying to pull the thing down to the center of the Earth. So let's fire this. Watch your ears. Is that too loud, or is that okay?
No, that's perfect, Dave.
Okay. Did you see the trajectory and it hit, right? That's the end of those people there.
Dave, you can zoom in on the Earth a bit, can't you?
I can.
Good. It's just the trajectory in red is hard to see.
Thank you.
Yeah, I can't see the red dots. Thank you.
Thank you. And if I slowed it down and did it again, it actually draws more dots. So I'll try to do it that way for now. When we do longer orbits, it takes too long. All right, well, what I'd like to do is I would like to bombard some people over here. So what do you think I should do to make the cannonball travel further along the Earth? What should I do?
Increase the initial velocity.
So I'm going to make the speed, the horizontal speed, I'm going to go from 0.5 to 0.8. So let's see what that does. Well, that was pretty good. So again, it's falling because of gravity. That's good. I want to get some people over here though. What should I do? Make it go a little faster? I would like to get down here though. Let's go a little faster.
Keep going.
You can see why I usually speed this up. Yeah, but I want to get down here. I want to get rid of the penguins. So let's see if we can. Oh, we're getting there.
I notice you're making very tiny incremental changes.
I am, because I know the number that's going to do the magic.
Right.
Oh, almost to Antarctica. So far, so good, right? Everybody with me? Gravity's causing it to fall, and it falls and it hits the surface. But if I go to the magic number, and these are all arbitrary speeds here. Look what happens. Now, how is that one different from any of the other ones? Each one of the other ones is a falling of the body, yes? What about this one? Well, this is exactly the same thing. It's falling too. But something is falling away faster than the body is falling, and that's the surface of the Earth. The speed at which we launched this last one, its rate of descent is less than the rate of curvature fall away of the Earth. And that's what an orbit is. See, when you talk to your students and you ask them what an orbit is, they're not going to tell you it's a body falling around the Earth. They're just going to say it's an orbit, gravity's. Well, gravity makes everything fall. Gravity never pushes, it always pulls, and it's always causing things to fall, always. And so that is what an orbit is. Now, if they don't believe that, ask them what happens to astronauts in space. When they're in space and they're floating around inside the space station, we say they're in a state of what?
Free fall.
Weightlessness.
Weightlessness, right?
Yeah.
Are they really weightless? What is weight but the force of gravity on you? Is there no force of gravity on them in the space station?
Right. Yeah, something like 90% of what they would weigh on Earth.
Exactly right, Chris. The force of gravity in the space station is about 92% of what it is on the surface of the Earth. If there's no gravity in space, they'd fly off in space, right? This is what happens when you get your science from the guys in the media. There's almost as much gravity in orbit as there is on the ground. The difference is, as Scott is saying, is that what's happening is they're falling. They're in free fall. So they feel like they have no weight, but they're falling around the Earth. The same as if you jumped out of an airplane with bathroom scales and put the bathroom scales at your feet. What would the bathroom scales read as you're falling through the air?
Yeah.
Basically zero, neglecting air resistance, right? But does that
Dave,
mean you have no weight?
not to take this too far out on the weeds, but I've heard some planetarians argue against the concept of microgravity. The press is always mentioning microgravity as what astronauts feel in space. And it seems like if you're truly in free fall, that's a silly idea, or maybe I'm thinking of it wrong. What do you think they mean by microgravity?
They're talking about like a relative gravity. Like when you're in free fall, it feels like you have no weight, right? It feels like there's no force of gravity. So the environment is such that it acts as if there's no gravity, but in reality, if there were no gravity, you wouldn't be falling around the Earth. My students often think there's no gravity in space. And so it's like, well, then why are the planets going around the sun if there's no gravity? When they understand this, they understand that an orbit is actually a body falling around. We're going around the sun, but when we're falling around the sun's surface curves away at a rate which is more than the rate at which we're falling. And so that's what an orbit is. Dave,
if I may just
Go ahead, Chris.
add a little bit, because I've been asked about the microgravity as well in my classes, and I tell them, I think it's just an attempt to acknowledge that there is gravity at work here, but they're not feeling its effect because they're not being pinned down to anything like we are here on the surface. However, I think it's a little bit of a misnomer because 92% of the gravitational forces there's nothing micro about that.
Yeah, it's all. It's exactly. It's a relative effect.
Right.
Yeah.
So it's not like, oh, they weigh just a little bit if they could stand on a scale. No, they'd weigh nothing, except for whatever normal force they're presenting on the scale.
Yeah.
So yeah, I tell them it's technically a misnomer, but it's an attempt to acknowledge that there is gravity at work here.
Right. Now I'd like to make a bigger orbit. What should I do? Increase my initial speed?
Yeah.
So let me just increase the initial speed. I'll kick it up to 1. Let's see what that does. We'll speed it up a little bit. And so we get more elliptical, because the people on the cannon on the mountain always get hit, but they have to duck and get out of the way. What if I want a bigger orbit? You won't see the dots probably. And they can go faster. Now, what if I go like too fast? You see this guy here?
Mm-hmm.
You see this guy here? There he goes. Can you see him? I don't think he's coming back. So if we took the time, which we're not going to do, this guy is tracing out a hyperbola, better known as he's gone. He's reached escape velocity. He's out of here. The one I like to do, the students, I say, what if you go like super fast? Goes super fast. Off he goes.
Mhm.
Bye-bye. Have a nice day. So it's kind of fun. Now, the other thing I like to do, zoom back in here again. This program has this really neat feature. So I say to the students, you know, when you throw a ball or a cannonball or whatever, this path is not arbitrary. What the thing was trying to do was orbit around the center of the Earth. To prove that, if we shut off collisions, now I'm going to make the surface of the Earth permeable. I'll go back to that first launch. Watch what happens. Not at that speed. See, that's the trajectory it was trying to do. It was trying to do an ellipse around the center of the Earth. Now, I'm not saying, please don't misunderstand. I am not saying that this is what will actually happen if you could go through the Earth, because this is a differential equation where as you go inside the Earth, the mass outside where you are actually pulls you the other way. So this is not what would happen if you could travel through the ground. But this part of your trajectory is part of an ellipse where you're trying to go around the center of the Earth, which becomes your focus of the ellipse.
Dave, I'm afraid this is going to be a terribly stupid question, but if the Earth's size were tiny, but its mass were the same, and you launched the cannonball from the same point,
yeah,
would it essentially trace this orbit?
Yes. Yep.
Yeah,
you
could
the
say
Earth,
like Newton.
the Earth acts like a point mass, Scott. So
yeah,
right. As long as you're exterior to it, once you get in, then you've got mass pulling you the other way, and the equation changes.
Right. I asked because to achieve this orbit, you can ignore the fact that the Earth has mass inside and outside. You can just pretend that its mass is a point at the center of this
That
orbit.
is, yeah, and that's exactly what the equations are assuming.
Okay, I thought so.
Yeah, and that assumption, Newton didn't want to assume that, so he did the math to figure that out and prove it, and that math we now call calculus. So he invented calculus to solve one problem, and then found out, hey, you know, this is pretty cool. I can use this to do a lot of stuff. So that's Newton's mountain. It's kind of a very, I find that when my students finally understand orbits as a falling body, and this is how Newton tried to explain it in the late 1600s, early 1700s. So if it's good enough for Newton, it's good enough for us.
Dave, do you play around? I'm assuming that your second input there after the speed is also your angle.
No, that's actually your y velocity. So let me make the x velocity.
Okay, yeah,
here.
right.
And if I just put in a y velocity and fire, it should just go straight up.
Straight up and down. Okay, great.
Or down, whatever.
Oh, that's right. You turned off the Earth.
Yeah, exactly. So,
Dave, are the values arbitrary, or are these kilometers per second?
no, they're arbitrary. It's a relative scale. Yeah. Any other questions? Would you find this useful for your students? I mean, I just find that this is why I wrote this, is because my students just weren't getting it. And what Newton has in his treatise is this exact Earth, but then he's got, you know, several orbits that look just like those. Just nicer to see them out and actually traced out. And
Any
then
idea what the C represents?
Sorry?
Is there any idea what the C represents?
Center.
Center, thank you.
Center of the Earth, yep. And then the last program is the sexiest of the three. That's why I'm saving it for last. And that's tides. Perhaps the most difficult concept to get across to anyone if you don't know vectors. So let me show you the workings of, and this program actually works with side touch. So anything I'm doing with my mouse can be done with a side touch, and that's really classy. So you got the Earth and the Moon, and the distance between them is not to scale. Their sizes are, but the distance isn't. I can grab the Moon and make it go around with my mouse. So that's fun. And you'll see why that's fun later. If I right mouse click, I can actually make the orbit smaller. And we'll see that that will be fun as well. Over here, you have all kinds of things which we'll be going through. You can actually make the moon half as massive or twice as massive to mess around with its gravity. And what we've built in is a mode where you can just click a button and it goes through what I call the lesson of how to teach tides. And that on the side touch, you just keep pushing the same button and you go through this lesson. So let's go through the lesson. It's not long, and maybe this will help people understand tides a bit. So the first, what we're doing is we're drawing a vector from the center of the Earth towards the moon. This represents the moon's gravity on the center of the Earth. Okay, so if I move the moon, then that vector is going to trace, right? Because it's always pointed at the center of the moon. If I move the moon in closer, what do you think is going to happen? That vector should increase, right? Because the length of the vector represents the magnitude of the force. So bring it further away, it gets smaller, bring it closer then, etc. So far, so good? Okay. Now, the size of the Earth relative to the moon's orbit is not negligible. So if you were to ask your students, if I were standing right here, would I feel more force from the moon or less? Or the same as the center?
It'll be more.
I should feel more because I'm what? I'm 4,000 miles closer to the moon, which is only 238,000 miles away on average. So 4,000 miles out of 238,000 miles is a significant amount. What about on this side? What would people feel on this side? They're now 8,000 miles away from the moon, from this compared to this side, or 4,000 away. This is going to be less, right? In the same direction, but less?
Yeah.
Okay. What if you were standing here?
Mm-hmm.
You're going to feel a force about the same as this, right? Because you're roughly the same distance, but it's going to be aimed differently, right?
Right.
So that's what the next thing does. Uh-oh, so sorry, the next thing actually makes the moon bigger. I doubled this mass of the moon, and the vector got twice as long. If I cut the mass in half, it gets half as long. Okay, forgot about that part. That's the part I want to do. I now have drawn a force vector at those four, what I call cardinal points, so to speak. The one closest to the moon, that's the greatest one. The one furthest from it, that's smaller. These guys are the same magnitude, but they're aimed directly out. So far, so good?
Mm-hmm.
Okay. And then, of course, you can do this. It's the students, they just like that. So they're going to point to wherever the moon is. What if I drag the moon in closer? What's going to happen? They're all going to get bigger, right? I hope. Or smaller if I draw it. So far, so good?
Yeah.
Okay. Now we're ready to explain tides. What the Earth experiences, what the Earth feels because of the gravitational tug of the moon. The moon is tugging this side of the Earth significantly more than this side, is it not? So it's pulling harder here, not as hard here, and even less hard here. There's a difference in gravitational pull across the diameter of the Earth. If we were to ask the question, what does the Earth feel? That, in a physics sense, is saying, what if I take this force at the center of the Earth and subtract it from each of these forces? That would give me what's called a center of force reference frame, which is equivalent in English. That's saying, what does the Earth feel? Because it feels a tug hard on this side, not as hard on this side. It's going to feel like the Earth is being stretched. Let me show you by actually putting in these orange vectors. The orange vector, you can see it better here. This is exactly the opposite of this central vector. What I'm going to do is I'm going to subtract the force the Earth feels at its center. I'm going to subtract that from each one of the 4 vectors. So obviously, if I do that at the center, that's going to give me a point, which is, that's why I'm doing it. I'm reducing it to what the center of the Earth feels. Here, subtracting, I'm putting the tail at the head, right? If you have a vector and subtract it, I'm going to end up with a vector that goes from here to here. What about over here? The vector over here is this long, but the vector I'm subtracting from it is this long. The difference is from here to here. From here to here, and over here, I've got this long force vector subtracting this one. It's going to give me a vector like this. So that's going to be the white vectors. Do you see the white ones? The white vector is the result of subtracting the center force from each of these vectors. Is this making any sense at all? Okay, so we can do this. This is being done every 90 degrees. What if we do it every 30 degrees? What if we do it every 15 degrees?
Mm-hmm.
Of course, my students will say, wait a minute, move them around. I want to see them all move. Okay, there it is, just to satisfy your curiosity. What happens if you move the moon closer? Then you get all kinds of fun stuff. Look at that. They just like to see stuff move. Okay, now, what I want to do is I just want to see the resulting white vectors by themselves. This is the differential gravitational force that the Earth feels from the moon. Okay. Notice that on this side, yes, it's actually bigger than this side. This, again, most people are never taught this. This differential gravitational force, which if we connect all the ends of the arrows, gives us this egg shape. This is your tidal bulge. It is not symmetrical. Tides on one side are indeed higher than the tides on the other side. And again, this bulge will be directed in whatever direction the moon is in.
Nice.
Yes? And if you bring the moon in closer, that's going to, right, make the tides go wacky. For those people in binary stars, you start to see your Roche load stuff. And if the moon is far away, that diminishes the effect of the tide. So far, so good? So where are you going to experience high tide? Where is high tide going to be? It's going to be here, yes, and
The opposite
over
side.
here. But this one will be a little higher than this one. And if you check your high tide tables, you will find that one tide is always higher than the other one. It's the one that's directly beneath the moon. Yeah, you didn't learn that in college, did you? Yeah, neither did I. It isn't a big difference. We're only talking a couple feet difference, but it is definitely different. They're not as high because the differential force is greater here than over here. So why do we experience tides roughly every 6.5 hours? Well, we go from low tide, which of course is here. Well, it's because the Earth is rotating. But the tidal bulge wants to stay lined up with the moon. And so the moon is, right, the moon moves 13 degrees per day. So this is what's happening. The tidal bulge is moving more slowly than the Earth beneath it. So this is why we don't get tides every 6 hours, right, from low tide to high tide, because the bulge is moving as well. So this is what's going on with tides. I showed this to a guy at a Mariner museum, and he almost killed me to get the program because he couldn't get his students to understand tides at all. And when he saw this, it's like, I got to have this program. So you can imagine how cool this looks on the dome. This is up at the zenith, and you can take your side touch and do this. Or you can take your side touch and do this. It's a very impressive graphic. And so that's tide. Now, be honest with me. Does that help you understand tides maybe better than you've ever understood it before? And that's why I wrote the program. this is why, I mean, trying to explain tides in a classroom, what's the question they always ask you? It's the same question everybody, why is there a bulge over here? You cannot explain that without going through what I just did. The tides are not caused by gravity alone. It's caused by a differential gravitational force. What I tell my students is, look, when I ask them what causes tides, what do they say? The moon's gravity. So then I say to them, well, if that's the case, why doesn't the sun cause bigger tides? Because the sun is pulling 160 times harder than the moon. Why aren't the tides caused by the sun? And then they just look at me like, well, I don't know. I never thought about that. It's because the sun sees the earth mostly as a point. But the difference in 8,000 miles compared to 93 million miles, the solar differential gravitational force is not as much as the moon's differential gravitational force. It isn't negligible. The sun does have an effect on the tides. It's not negligible, but the moon is the major cause.
Dave,
So
do you
what do you think?
also teach tidal lag or anything like that? Like the tidal friction on the Earth bringing the bulge ahead a little bit? Do you?
You can. Yet you can. I mean, because you can see that the Earth is turning at a different rate than the tidal bulge, so that's going to cause the tidal friction, which is why the Earth basically is slowing down, and
Right.
has been ever since it was created.
I point out that so since I teach at Towson, we're relatively close to the water actually, and so a lot of my students have buddies who have boats, and they notice, or they, a couple of them have asked, well, how come there isn't a high tide when the moon is on the meridian? Which is a great question, and I love to address that partly through the fact that the tidal bulge is being dragged ahead a little bit.
Right. No, it's a very good point.
Yeah.
I'm just trying to get them to understand why the tides work at all and why there's a bulge on the other side. That to me is the most important thing to get across.
Agreed. That's really cool.
Very good point. Are there any other questions? So if you want this for your side dome, you need to contact Spitz and you purchase it through Spitz. And if you want the desktop version, then you would contact me directly because Spitz doesn't sell the desktop version. That, in the sense of the COVID issue, if you wanted to put this online and teach your students using this with your desktop or laptop, you would need the desktop version, which I sell separately. Okay, well, that is the end of our session, and unless there's any other questions, we're supposed to be done.
One quick note on your schedule document, if it's still showing advanced user session as one of the options next hour, just reload that browser page. Apparently that one bit Google didn't auto refresh. Should be showing Dan Z's show production tips part 2. And get your break, and we'll see you next hour.
Thanks, everybody. I hope you enjoyed that.
Yeah,
Thank
good
you.
job, Dan. Well done.
Mr. Bradstreet, how do we contact you if we want the desktop version?
My email is in the list of attendees. So you just send me an email.
All right, sounds great. Thank you.
Sure, you're welcome.
Hey, Chris, I have a question for you.
Yeah.
Did you say that Michael's session is now been filled in? His part 2 has been filled in on that, or am I?
No, the what was on, so it's TLE Beyond the Basics is track 1.
Yeah.
Track 2 had been showing advanced user session for some
Okay.
people. It's Dan Z's show production tips part 2 is what that is.
Okay, great. Thank you.
All right, see you there.
Okay,
All right.
very good.